this video, we are going to study the concept of absolute and conditional convergence. And we're going to begin by stating a theorem called the absolute convergence test. This result says that if we consider a series and we consider the absolute value of the terms of the sequence associated to it, and this series converges, so the series where the terms are all in absolute value, then we can conclude that the series with the terms without the absolute value converges as well. And from here we get to define what absolutely convergent means for a series. So, definitions, we say that a series sum of a's to n is absolutely convergent when the series with the terms with absolute value converges. So this is our new concept of absolutely convergent. It's not only that the series converges, as the test says, it's also that it even converges if we take the terms with absolute values. If this is not the case, so if the series converges, but the series with the absolute values does not converge, note that from the test this will happen because the test is not in even if and only if, it's only in one direction. It only says that if with absolute values converges, then without it also converges. But we could have cases where, and we'll see examples where without the absolute value converges, but when we put the absolute values we miss the convergence. But in this case, so if we have the series that it is converges, but with the absolute values doesn't, then we say that it is conditionally convergent. And then our series is conditionally convergent. So if we have a series where there are some terms that are not necessarily positive, then we have three possibilities. Either the series is divergent, either it is conditionally convergent, or it could be absolutely convergent. We are going to quickly see what is the idea of the proof of this result for the absolute convergence. So the idea is the following. We know that when we consider the terms of the sequence an, they're going to be less or equal than the terms with the absolute value. That's clear. The problem is we would like to compare the series associated to these two sequences, but in principle, this sequence with the ANs will have negative terms, and we don't want that to happen because we want to apply the comparison test. So we're going to solve this problem by adding on both sides of the inequality one more time the absolute value of the ANs. So now we are sure that 0 is less or equal than the absolute value of the ANs plus AN, which is less or equal than the absolute value of the ANs plus the absolute value of the AN. So we can write 2 times the absolute value of the terms AN. So this means, since we know that the series with the absolute value converges, it means that if we take 2 times the terms, this also converges. And since we are talking about a series of positive terms, by the comparison test, we also will have that this series where the terms are the AN plus the absolute value of the AN, this would converges as well. Okay, but this is not the one we want to classify. We actually want it just without this absolute value of AN, so we need to get rid of that. So we are going to consider the series that is negative the series of the absolute value of the ANs. And this one converges as well. Yeah, the sum is just going to be the negative of the sum of the series of the absolute values. And now we can sum the two series we have over here because the sum of convergent series is convergent as well. And the result, we took this negative, so the term with the absolute value of an cancels as we wish. So the series of the an converges. And that was what we wanted to prove. Let's look at the first one of our examples. We have the sum from 1 to infinity of -1 to the n over n factorial. We want to see whether this series is absolutely convergent, conditionally convergent, or divergent. My intuition says that this is going to be absolutely convergent, so I'm going to consider the series with the absolute values. So -1 to the n over n factorial is going to be under absolute value. So that means that we are just considering this series of 1 over n factorial. And this is the one that we want to prove that it converges. And if we can do so, then we will be done. Since we have factorials, I'm going to try to apply the ratio test. The term an is 1 over n factorial. And this is always different from 0. We are taking n greater or equal than 1. So I need to look at an plus 1 over an, the ratio between two consecutive terms of the series, and that's going to be 1 over n plus 1 factorial over 1 over n factorial, which is n factorial over n plus 1 all of it factorial, and canceling n factorial, we are left with 1 over n plus 1. And if we consider the limit of this as n approaches infinity, this is 0, which is less than 1. So then by ratio test, the series we are studying converges. So the series we had to classify is absolutely convergent because we show that it converges with absolute values. Absolutely convergent. And that was part A for us. For part B, we have to consider the sum from 1 to infinity of, we have a factor of -1 to the n plus 1 times 2 to the power of n over n squared. Okay, when I look at this, the first thing that comes to my mind is that when we compare the 2 to the power of n and the n squared, the 2 to the power of n, this is winning. This is stronger. So I think we are in a case where the sequence whose series we are trying to classify actually does not have limit 0. So if that's the case, we can just apply the n-term divergence test and conclude that this series is divergent. So let's look at the limit when n approaches infinity of, we have -1 to the power of n plus 1, and then we have 2 to the power of n over n squared. Okay, so when n is even, then we are going to get the terms -2 to the power of n over n squared, and when n is odd, we are going to get the ones with the positive sign, so 2 to the power of n over n squared. So if we can prove that the limit of 2 to the power of n over n squared is infinite, then this series will be alternating between, the sequence, will be alternating between values that are getting bigger and bigger and positive and values that are getting smaller and smaller negative. So the limit of this is not going to exist, so it's not going to be 0. So let's look at what is actually the limit of 2 to the power of n over n squared as n approaches infinity. Well, we know that both the numerator and the denominator are approaching infinity. So I'm going to look instead at the function associated to this with limit x approaching infinity, so 2 to the power of x over x squared. Because we have then a limit of functions of the type infinity over infinity, so we can apply L'Hopital. And we are able to do so because this is approaching infinity and this is approaching infinity too. And we are talking about continuous functions without any problems. So by taking derivatives on both the numerator and the denominator, we are going to have a factor of logarithm of 2 to the power of x, and then that's going to be divided by 2x. And we're still in the case that we have infinity over infinity. So we're going to go ahead and apply L'Hopital one more time. This time we are going to have one factor more of logarithm of 2. So this square 2 to the power of x divided by 2. So now the denominator is a constant, a positive 1, and the numerator is approaching infinity. So this limit is actually infinity. So this is approaching infinity, and this is approaching negative infinity, which means that the limit we were trying to find is not 0. So that means that the series we were trying to classify is divergent by the n-term test, n-term divergence test. And we're done with B. I'll let you try C, this last one alone. I'm going to give you the hint that you're going to use the fact that when you consider the limit of sine of x over x as x approaches 0, this limit is 1. I mean, at least the way I thought about solving it, it involves applying that limit. So I'll let you try that, and I'll tell you as a hint that the result is going to be that this series is actually conditionally convergent.